In this video, we are going to work through the assumptions of the independent samples t-test. Working from the previous video, you should be sure to have two variables in your environment. The first variable should be the data that we read in and then saved to a variable. The second should be the descriptive statistics that come from running the summary function on the data that you brought in. Now we are going to move on to this topic, so go ahead and type this topic as a heading: Independent Samples t-test Assumptions. The first question you might ask is, what is an assumption? And what is an independent samples t-test? T-tests are used to investigate differences between two sets of means. A mean is an average of a group of numbers. There are two different types of t-tests. The first type that we'll go over today is the independent samples t-test. Independent samples t-tests look at the difference in the performance of two different groups. In our data, if we take a look at the data frame, we can see that we have two different groups here. And like we just went over, the independent samples t-test looks for differences between these two groups, between the averages of these numbers. In our case, we're looking at group 1, which has explicit feedback, and group 2, which has implicit feedback. These data are not real. They are only for educational purposes. So keep that in mind as we go through them. Imagine that this study was on the influence of explicit versus implicit corrective feedback on the motivation of learners. Each of these numbers means a particular learner in this group had this level of motivation. Similarly, in this group, these each mean a different level of motivation. The higher the number, the more motivation that this participant, this language learner, had. Because this is an independent samples t-test, these two groups are different groups. Now, let's move on to the assumptions. Before we do that, quickly, we'll go over in the next couple of videos after this set our paired samples t-test. And paired samples t-tests look at the difference between two performances by the same group. But we won't go over that today. What you see here is the workflow of doing a statistical test and running a statistical analysis like we will run today. We will focus on these three items: checking the assumptions, running the test, and interpreting the results today. But remember that there's also item and reliability analysis that you will learn about in a different video. And then there's reporting the results, which means writing the results in a form that other people can understand. What we'll go over today is checking the assumptions. An assumption is like a requirement for a given statistical analysis. Think of an assumption like a prerequisite. You have to think about the assumptions and meet the requirements of the assumption in order to be able to use the test to make any kind of decision or use the numbers from the test to make meaningful conclusions about what the numbers mean. In the case of the independent samples t-test, we have 1, 2, 3, 4, 5, 6 assumptions that we will go over. Now, when you're just looking at it like this, it may seem like an overwhelming and scary amount of information. That's a natural feeling, especially if you're new to statistics. It's okay though. We will go over them one by one and I will explain what they mean very simply, and I will show you how to check to see whether or not the assumption has been met in R. The first couple of assumptions relate to how you ran the study to begin with and how you collected your data. They relate specifically in this case to the independent samples t-test. Feel free to type along with these or pause the video in order to be sure that you get the information. First up, with assumption number 1, you have one dependent variable that is measured at the continuous level. What this means basically is that you have one variable that you measured, you have one outcome variable that you measured at the continuous level, which means it consists of numbers that aren't forced into any particular buckets. In our example, we have met this assumption. As you can see, we have one dependent variable. Our dependent variable is motivation, and it's measured at the continuous level. We know this because we aren't forcing these values to be just 5 or just 6 or just 7. These values can be anything within the range of our measurement. So this variable just happened to come out to 5.49, but it could have been 5.4913, and it would still be good to us. Now for assumption number 2. You have one independent variable that consists of two categorical independent groups. In other words, a dichotomous variable. We just looked at our dependent variable, which is what we measure as the outcome. Here it's motivation. And our independent variable is how we group our learners. In this example, we have two groups. One group is explicit feedback and the other group is implicit feedback. This means that we have one independent variable, and that independent variable is corrective feedback. And we've split it into two categorical independent groups. Categorical meaning we can just place these categories and split them into two, meaning it's dichotomous. And that they're independent means that we are not looking at performance 1 and performance 2 of the same learner. No, these are two different learners in two different groups. Assumption number 3. You should have independence of observations. This means that there is no relationship between the observations in each group of the independent variable or between the groups themselves. This relates to how you ran the experiment in the first place. So you'd want to make sure that you meet the independence observation. Let's move on to assumption number 4. There should be no significant outliers in the two groups of your independent variable in terms of the dependent variable. This means that none of these numbers should be extremely different than the other numbers. If any variable is extremely different, it means it is an outlier. Outlier means it is outside of what you would expect it to be based upon most of the other data. We can check this assumption with a box plot. A box plot is a visualization, a graphic, that you can look at to check if you have any extreme outliers. This is the code that we will use in order to look at the box plot. First, you type box plot, open parentheses, and then each of these is one of these columns. So you can see that first we put the name of the whole data frame, then a $sign, and then the name of the column, explicit feedback, and then comma, and we do the same thing for the other column, implicit feedback. This code will let us see both columns in the same graphic in a moment. Go ahead and type out this, save it to a variable, which I call boxplot both groups. If I am going too fast, feel free to pause the video and type to catch up. When I run this code, you can see that a box plot appears. Each of these boxes represents our data. Column 1 is represented in this box. So this is explicit feedback here. And number 2 is implicit feedback. We won't go fully into depth about what the box plot means here, but you can look it up online. What we're interested in the most right now is that there are no significant outliers. A significant outlier would appear as either a circle or a star. A circle would be an outlier that is okay. So a circle would not be a significant outlier. A star would be an outlier that is significant and that could potentially cause our results to be unreliable. Here you can see that we have no circles. Even if we did have circles, it would be okay because those aren't significant. But we don't have any circles and we don't have any stars, so we can see that there are no outliers in this data.